Okay, welcome back to our last lecture. I am going to keep this somewhat brief. I know the last one was a little on the long side. If you want, you can go ahead and open up that data file called Home Runs Major League Baseball, which you probably opened up in the last video, but we didn't use. And go ahead and import that into StatCrunch if you want. This is going to be kind of a light sort of lecture, okay? I don't really think I'm going to necessarily test you or even give you homework on this. However, it is useful. It may come up in various forms, the sort of things we're talking about. And in the next week's module, we're going to definitely touch on some of these applications, which are going to be really important. So you also don't want to blow this off. So the first thing I want to look at is this problem we talked about before, and that is comparing two things or making a decision between two things that can't be directly compared. And so we're going to go back to this problem about who was the better home run hitter, Barry Bonds or Babe Ruth. Okay, both great baseball players, but we can't compare them directly because they played in totally different eras. So the way that we're going to compare them is we're going to ask which player was more dominant. In other words, we're going to look at their relative standing with respect to their peers. And the way we're going to do that is we're going to look at the year that they were considered most dominant. So it happens that Babe Ruth in 1920 was most dominant among the other players, and Barry Bonds in 2001. So how do we do this? Well, this data set that you're looking at, it was obtained from ESPN, so the data set's valid, it's of good quality, and it contains the home run totals from all the years in which Babe Ruth was dominant, 1920, and Barry Bonds was dominant. And what we're going to do first with data, after we've looked at the data, and I've already looked at it and made sure that all the data values are valid and whatnot, is we're going to go ahead and make a side-by-side box plot. And what you can see is that Babe Ruth is much more dominant than Barry Bonds. There's really no need to even run any sort of statistical test, okay? I mean, this is Babe Ruth. He has 54 home runs. The next closest person has 19. And Babe Ruth has close to 3 times as many home runs as the next closest player. If you look at Barry Bonds, he hit more home runs than Babe Ruth, but the next closest player, Mark McGwire, really wasn't that far away. So clearly, Babe Ruth is more dominant, okay? He's so much more better than his peers. Now, we want to get a sense, okay, a little better sense of how far away Babe Ruth really was. So we're going to go ahead and compute the z-score. So what we're going to do, we have to make it a fair comparison, okay? We have to remove these players from the data set. We have to remove especially Babe Ruth, because what Babe Ruth is going to do is Babe Ruth is going to inflate the mean, right? Remember how we compute the z-score? We take the data value minus the mean. Well, Babe Ruth is going to inflate the mean, okay? So we want to look at the average without him of the other players and then compute his z-score relative to these values. Barry Bonds will inflate it, but only slightly, okay? So we go ahead, we compute these values, okay? I'm going to go ahead and look at the variable home runs. I'm going to group by year and look at the mean and the standard deviation. And let me just go ahead and do that alongside you guys. So we go to stat, summary stat column, look at home run, and I want to group by year. In other words, I want to compute the summary statistics for each year. That's what this means. I'm going to look at the sample size, the mean, and the standard deviation. It's always a good idea to put the sample size in the summary statistics, okay? And there we are. And we can now go ahead and we can compute the z-scores for Babe Ruth and Barry Bonds, okay? So let's go ahead and do that. I don't think there is a way to compute the z-score in StatCrunch. There kind of is, but it's not particularly useful. You have to do a lot of other complicated things. So we can just do this calculation by hand. Okay. So again, the z-score is going to tell us how far away from the mean, okay, each player is. And when we do that, here's what we have. So the summary statistics from 1920, we had a mean of 117, standard deviation of 2.66, and Babe Ruth has a z-score of 19.8. Okay, that's amazing. I mean, I've seen a lot of data sets, and I've seen very few where a data value actually comes from that population and the z-score is that large. And if you look at Barry Bonds, his z-score is large, but it's less than half of Babe Ruth's. If you use Chebyshev's rule, which I didn't get into, I had at the end of that last video, and I let you guys read if you wanted to, you'll find out that there's less than a 0.3% chance you would get a player as dominant as Babe Ruth. And in the case of Barry Bonds, it's only 1.4%. So both graphically and numerically, Babe Ruth is by far the more dominant home run hitter in his era. Okay, so let's look at a second problem now, which is process control. Sometimes people call this quality control. And this is something that you see a lot in manufacturing and industry. So suppose you're checking the voltage on an aircraft. You need to know when the voltage is abnormally high or low. Okay. You want to know if you should buy a penny stock whose price has increased. I actually mentioned that problem in the last video. And both of these problems, both the stock market problem and the aircraft maintenance problem, have something in common. They're both what we call process control problems. So when we look at quality control, here's the idea. We know what the mean and the standard deviation are for a particular variable if nothing out of the ordinary occurs. So for example, I can take voltage readings on aircraft that are operating properly. And again, there's going to be variation, and most likely it's going to look like a normal distribution. And so I know that if it's operating properly, it should have this sort of variation about the mean. And I can compute the mean and the standard deviation. Okay. And what we're going to do is we're going to go ahead and we're going to make what's called a control chart. We're going to plot the mean on this center line, and we're going to take readings at various times. They could be readings of an aircraft voltage. They could be readings of a stock price, right? This is kind of like a time series. And when this value goes 3 standard deviations away, we know that it's very unlikely to occur. And that we know from the empirical rule. And that's when we're going to say the process is out of control. Okay? So again, these fluctuations about the mean, they have a normal distribution, and so we can use this empirical rule here. We know that it should only go beyond that 3 standard deviation mark, not more than 2.5% of the time. And this is the idea behind a control chart. And so if you're manufacturing something and you're pulling things off of an assembly line, and all of a sudden you have a particular product that's more than 3 standard deviations away from its spec, you're going to probably stop the production line and do a little more testing because the process is out of control. Okay. The last thing we're going to look at is called hypothesis testing. And so this is kind of I'm not going to say it's a frivolous example. It's kind of a fun example, okay? This did not come from real data. This is just something I'm making up. But it's based on a real experiment from another context. And so we want to know, is chivalry dead? In other words, is courteous behavior of males towards females a thing of the past? And so let's suppose that we did some sort of experiment, okay, where the same female approached the doorway when a man was entering and was 8 feet away. And it was found out of the 28 males in that study 19 of them opened the door for the women. And we asked the question, is this evidence that males are still chivalrous? And this is a problem in what we call hypothesis testing. We're not going to get to hypothesis testing till probably at least another 2 modules down the road. However, there's a really important concept and a very difficult to understand concept that we are going to talk about next week that's an integral part of hypothesis testing. And this is one of the main reasons why I made this particular lecture. So what we want to do in hypothesis testing is consider 2 hypotheses. The first is the null hypothesis. This is what we would believe if there was no evidence. The other is the alternative hypothesis. It's what we're trying to prove. If you read old papers, you'll sometimes hear it called the research hypothesis, because it's the thing that we're trying to prove in our research study. So what would we assume about males if we had no information? We would assume they're indifferent. They don't care one way or the other. What are we trying to prove? We're trying to prove that they're chivalrous. Now, we can't do a statistical study based on these 2 characterizations. Okay, this is too airy-fairy, too qualitative. We need to make this question quantitative. So I'm going to make this a question now about the percentage of males in the population that would open the door for a female. This is going to be now kind of morphed into a question about the population parameter. So I'm going to say that the male population's indifferent if the percentage of all males in the whole population that would open a door for a female would be 50%. And on the other hand, I'm going to say that males are chivalrous when more than 50%, the majority of males, would open the door for a female. Okay? Now, how do we answer this question? We only get one sample, right? So how can we tell from that one sample if it's 50% or greater than 50%? What we want to do is we want to go back to this concept that we talked about when we were discussing sampling. Remember, we said that samples estimate populations. And more specifically, the sample statistics estimate the population parameter. Notice I couldn't get all males to participate in that study. So what did I do? I took a sample. I took one sample. Now I know that if I'm sampling correctly, if I'm taking a large enough sample and it's randomly chosen, my sample statistics, my estimators, should be centered around the number I'm trying to hit, the parameter, okay? And they should be relatively close. That's what it means to be a good estimate. You're not very far away from the true value. And I want to take this picture and now look at how it appears in a statistical context. What we do in a hypothesis test is we assume the null hypothesis is true. We assume that the percentage of males that would open the door is really 50%. And what we do is we consider what would the population of sample estimates look like if it came from a population where the parameter was really 50%. This is a really difficult concept to wrap your head around. So I'm asking, if the population percentage really was 50%, and I kept taking random samples over and over and over and over again, and every time computing the sample percentage, and I looked at all of these sample percentages I would get, they would look something like this, right? They would be centered around 50% and be kind of clustered around there. Now, I didn't see 50%. I saw, what did I see? I saw 19 out of 28, which is 68%. And this is where that 5% criterion comes from. What I want to know is if our sample really came from a population where the percentage was 50%, How likely am I to see my observed percentage of 68%? How likely is the same as percentile? So what I'm going to do, and what we're going to do in the next two modules, is we're going to learn what this distribution of sample estimates looks like. And it has a special name. It's called the sampling distribution, because it's the distribution of estimates I get if I keep sampling over and over and over again. This is a hypothetical distribution. We can never obtain this. However, we're going to see that probability theory tells us what it is. And I'm going to use the result from probability theory, and I'm going to find the tail of this distribution that the green dots form, and I'm going to find the percentile of my value in this distribution of sample estimators from the population where the population percentage is 50%. And if the probability that I could get this value, if it came from this collection of sample estimators, is less than 5%, we're going to say we have a statistically significant result, because this is strong evidence for the alternative hypothesis. In other words, something significant happened. And we're going to flesh this out over the course of the next couple modules. But this idea of a sampling distribution is incredibly important in statistics. Everything that we do hinges on that. And we're going to come back to this concept over and over and over again. And we're going to flesh out the details of what this distribution is, how we compute this percentage, and how we make this decision. So this is a really interesting place to end. And like I said, we're going to pick up in the next module talking about this all-important sampling distribution. Okay, thanks for watching, and I hope you enjoyed. And if you have any questions about the homework, feel free to ask.